Welcome back to CS 402 with Professor Cheng. It's Wednesday, July 30th, 2014.
Tomorrow night, and again, the usual stuff. If you have code from previous semester, don't copy from it. The grading guideline is the only way we will grade. After your submission, make sure you verify your kernel submission. You don't want all your hard work that goes to waste. Okay. And again, a reminder: kernel 3, you got to test every branch of your code, and demonstrate that by using the correct DBG statement, using the right format. The final exam is next Monday during class, and we will cover everything up to the end of today's lecture. So my plan is to cover the very important topic of scheduling today. Hopefully, I think I should be able to finish the whole thing, and if we finish a little earlier, we'll finish the class a little earlier. Hopefully, I can cover everything. Minus the midterm coverage and plus kernel 2 and 3. Okay, so last time we have, we're talking about microkernel, and we're at this picture showing you how message passing, looks like, and sort of give you an idea why this is so slow. That's why sort of microkernel is really not popular these days. There's one more detail I need to explain. So this is done in the CMU mock machine. Is that the way that these that you get to talk to these message ports is actually sort of an interesting way of doing things. I think when we talk about the introduction to operating system, we said that the common system that we use, they all have one thing in common, is that the owner of a file decide who gets to access these files. Okay, so for these ports, so it turns out the way it's done is a little different. So I'm going to sort of briefly describe how do you get access to one of these ports. Okay? So the idea over here is that when you create a port, along with that particular port, you create what's called a capability that goes with that port. Okay, so the capability is something that allows you to talk to that port. So if you think about cryptography, it's like a key. Once you have a key, you can send encrypted messages to this port, and then whoever who owns the other key will be able to decrypt the message. Okay, so this capability is something that you can actually pass around. Okay, if you have a capability you want to give other people access, well, you just make a copy of the key. Okay, so this is a very different way to provide security. So in a way that the person who created this file no longer can control who can have access. Okay, once you create these keys, you pass them around, you lost it, somebody else will find a copy of the key, and all of a sudden they have access. Okay, so this is sort of a different kind of flavor of operating system where you can get access. So in this example, if you need to talk to the server, then you need the key, for accessing the server. And the way you get this key is that you make a request, and the operating system will decide whether you're allowed to access this guy or not. And if you do, then you get a copy of the key. Okay. So in our example that we had before, when the client wants the server to talk back to the client, what happens is that the client also create a response port, and together with the response port, they also create a capability for accessing the response port. So when it talks to the server to say that, I'm making this particular request to read a file, to write a file, when you're done, respond to this particular port. So what it means is that this capability that you create with this response port also needs to be passed to the server so that the server know how to respond. So when you send the request message, you can pass along that copy of your key and send it to the server. So later on, when the server is ready to respond, what it will do is that it will use the key that you pass to it and will be able to generate a response by writing to the response port. Okay, so the way that the kernel sends a response back is to present that capability to the operating system. Says, look, I have access to write to this port. Let me write to it. All right. So this is sort of a different way of dealing with things. All right. So that's really a brief introduction. So chapter 8, the security chapter, actually talks about capability in a lot more details. But unfortunately, we don't cover this this stuff. But sort of one of the reasons we don't really cover chapter 8, 9, and 10 is because this is sort of an introductory operating system class, and we have classes that deal with security system, CS570, networking, CS551, distributed system. I guess that's right now we don't really have a class like that, but networking system is kind of a distributed system. Okay, so chapter 8, 9, 10, we're sort of covering in some other classes. So that's why in this class we sort of focus on 1 through 7. All right, so the last slide over here basically says that microkernel has been tried many times, and then in the end, because of poor performance, people pretty much abandon, microkernel. Okay, I mean, not completely abandoned. The GNU people are still trying it, and maybe there are, people who's willing to use a system like that for all the advantages of the microkernel. It's more reliable, things like that. All right. Okay, so now we're done with microkernel, and we're going to talk about the last topic, in this class, which is, scheduling. Okay, so I guess when you finish taking the operating system class, people expect you to know, all different kinds of scheduler. So in this class, we're going to cover, quite a few different schedulers. Here are some of the, the list. We're actually going to see a more complete list in a few slides. So the goal of scheduling, so over here, so that's one of the problems with scheduling is that there are many different goals, and the goals might be conflicting. Okay, so you can't really achieve all these goals, so you try to pick some of the stuff that's important to you and, try to build a system around it. Okay, so for example, one thing that you might want is to maximize CPU utilization. Okay, I guess from warm-up number 2, you have this idea of, utilization, right? So it's the percentage, the fraction of the time a resource is busy. Okay, so you want the CPU to be as busy as possible because the CPU is doing a lot of work, right? So you don't really want the CPU to go idle unless it has nothing to do. Okay, so we put the CPU to sleep to save power if there's absolutely nothing to do. Okay, so in general, if we give the CPU a lot of work to be done, we want the CPU utilization to be as high as possible. Okay, so that's one goal, right? You can try to maximize your CPU, but that's just a number between 0 and 100%. There's not much you can do with that. All right, number one, another goal is to maximize throughput, and throughput can be defined as jobs per second. Okay, so you want the job per second of your operating system to be high. So what's a job, right? So if you think about, scheduling a thread, right? So let's say that this is time. Okay, you schedule a job into the wait queue, right, or the run queue, because this job or this thread is ready to execute. It's only waiting for a CPU. Right? Well, when you get on the run queue, that means you're done waiting for anything else. You're only waiting for the CPU. So now it gets on the run queue, okay? And then it takes a while for you to get to the CPU, and then you run in the CPU for a while. So let's say that we're doing non-preemptive operating system. So you run as long as you want, okay? And eventually, you need to go do I/O, right? So you go block to do an I/O. You wait on a different queue. So at this point, you move to a different queue, and you start waiting there for whatever thing that you need to do. Could be a mutex, could be I/O system, could be other devices. But eventually, when you're done, you're back in the run queue again. Okay. So in this picture, we sort of call this one job. Okay. This job started when it gets on the run queue, and then eventually it gets out of the CPU into the system, and eventually it will come back as a different job. Right. So one thread is going to be run as many jobs. We want the throughput to be high. So how do you make the throughput to be high? mean, assuming that this thread has to have this much CPU time running on the CPU, so there's really nothing you can do about it, right? What you can do is to make this time small, okay, and make this time small, all right? Well, of course, you can get a faster CPU, then you have faster throughput, but otherwise, you need to cut down all the CPU overhead to make this, this a high throughput system. So what you want is you want to minimize the response time. Okay, so what's a response time? Response time can be think of as the time between the time you get on the wait queue and the time you leave the CPU because you're waiting for block I/O. Or some people will define response time as the time that you get into the wait queue until the time you're ready to come back to the wait queue again. Okay, so there are different definitions. This time is called waiting time. Okay, in the textbook, it sort of defined the wait time as the time that you wait in the run queue before you execute again. But later on, they changed the definition and to say that, well, the wait time is actually the time once you get on the wait queue and then until the time that you get out of the CPU. Okay, so some of these definitions are kind of vague. It really depends on how you define it. So if you need to talk about things like waiting time or response time, you really need to define exactly what you meant. Okay, and you can even talk about response time as an interactive response time. I'm typing you a command, on Nunkey, okay, and that command takes some time to come back. So maybe at that time that you have run many jobs on the CPU, and eventually you're going to come back with a prompt. Okay, so that will be your interactive response time. Okay, when you're using a browser, you click on something until the browser returns again. Well, that's your interactive response time. Okay, so these words are kind of tricky. But sort of people talk about it all the time, minimize response time, minimize wait time, but you need to be very, very precise. Another thing that needs to be very precise is the term fairness. Okay, what do you mean by fair? You want to build a scheduler that's fair. What do you mean? So exactly, so it turns out that these terms are very vague. Okay, so when we're going to define it, we need to be very careful. Okay, one simple definition, is to assign equal proportion of CPU to threads. Okay, is that a good definition of fairness? Okay, what if you have a process that runs 100 threads and another process that runs only one thread? Okay, so should you, say that, well, you want to assign equal proportion of CPU to processes? But what about one person run many processes on Nunkey? Then is that being fair? Okay, then if you want to be fair per person, how do you track down a person? Okay, somebody might be logging into your account and running their jobs. So the fairness actually is very, very difficult to define. Okay, so the operating system can only do what it can do in order to define some of this fairness. For interactive jobs, right, you want the response time to appear to be fast. You click on the web browser, and then it comes back. You want that to be fast. Some of the applications are called real-time application. You want these systems to be responsive. You have a control system that try to control a nuclear reactor, and you want to do something, then it better respond very quickly. Okay. Scheduling is very important because its effect and how well it's achieved all these goals can be felt by the user. Okay, if the user wants a high throughput system, but you give them sort of a fair system, the user is not going to be very happy. Okay, if the user wants a timely response system, don't give them something, just have simple high CPU utilization. Okay, because they can actually feel it and say, hey, something is not going correctly. And in that case, they will go to another vendor that can provide a better operating system, to match their needs. All right, so I mentioned real-time application, right? So real-time, what is real-time? Okay, so real-time is actually defined very specifically as something that must be run by a deadline. Okay, if you want to run a job, you say, well, this job better finish by a certain deadline. Then that makes it a real-time operating system. Okay, so can you do that on Nunkey? You say, hey, I have a program, I have to finish running this by a certain time. Is Nunkey going to say, okay? So Nunkey is not a real-time operating system. Okay, so it doesn't really know how to do this. Okay, given a deadline, it doesn't know what to do with it. Real-time system also can divide into two kinds. One is a serious, real-time system. It's called the hard real-time system. And then on the opposite side, it's a soft real-time system. Okay, so real-time system, if it's okay to miss the deadline once in a while, then it's called a soft real-time system. So even if you have a deadline, okay, you can miss it, right? I mean, we do that all the time when we watch YouTube video. The video will get stalled. Is that okay? I mean, nobody dies if it stalls, right? So it's okay, right? Because what you do is you recover from it. Okay, so for audio and video across the internet, but these are soft real-time system. The deadline, if you meet the deadline, then the application will look like it has good performance. You don't have hiccup in your video or your audio streams, so that's desirable to have. Okay, but if it doesn't really meet the deadline, you miss a frame, you're gonna get a hiccup on the screen, or like if you watch TV, you will see the screen have these squares all over the place because your system cannot keep up with meeting the deadline. Then you recover from it. Okay, but you would like the system not to miss deadline. For hard real-time system, missing a deadline means disasters. Okay, so for example, if you have something that controls a nuclear reactor, you're supposed to do something to it, every millisecond, and you miss a deadline. Okay, that might not be okay. All right, so these things are much more serious. So for soft real-time system, right? We use the general operating system to take care of this. So they can be taken care of by general purpose operating system because missing the deadline is not very serious. Okay, if you want to not miss the deadline on a hard real-time system, you better choose a good operating system. And the normal operating system that you use today is not going to cut it because they don't understand deadline. Okay, so you have to use a scheduler that will actually make sure that things are run before their deadline. Okay, so these require specialized operating system. So I guess in this class, this is sort of the only place that we talk about things that are done for specialized operating system. Okay, so there are schedulers for these kind of jobs. So we're going to sort of talk about this towards the end of today's class. Okay, we're going to look at a bunch of algorithms today. This is a big list. Okay, some basic scheduling algorithm, some priority algorithm, some fair algorithm, and then a couple of real-time scheduling algorithms. Okay, we're going to focus on just the run queue. Okay, we don't really care about all the other queues, right? So a job get on the run queue, our scheduler kicks in and decide who to run next. Okay, and then it's going to run in the CPU. Maybe it will get preempted. It will not get preempted. Okay, but once it leaves the CPU, then we don't worry about it anymore. Okay. All right. So we're going to manage the run queue. So the scheduling algorithm is simply looking at the run queue, and the run queue can get a little complicated. All right. So first, we're going to look at the simple case, non-preemptive, non-interactive jobs. Okay. So or people call these batch jobs. And we try to schedule these jobs, right? So in this case, we have a job that comes in, way inside the run queue, it eventually gets to run, and then it can get blocked in an I/O. Okay, so this case is, this thread gives up the CPU voluntarily, okay, and then it will block on the I/O, and eventually it come back as a new job, okay? And we want to, schedule jobs like this, okay? We're going to run them one at a time without any preemption. Okay, and we're going to assume that the running time is known. Okay, if we know, when this job runs in the CPU, how long it will take, what will we do? All right, so keep that in mind. So let's start with a very simple scheduler, which is what's used in Unix, right? It's just a simple queue, first in, first out, first come, first serve, right? The FIFO queue. So this is not time anymore, right? This is the queue itself. Sometimes we sort of draw it like this. Okay, first come, first serve, meaning that you take the first job on the queue, and that's the one you're going to run on the CPU. Okay, and that's how some of the I/O queue works, how the mutex queue works. Condition variable, that's pretty much how it works. Okay, if you use the first come, first serve scheduling discipline. All right, very simple discipline. All right, so we can look at some performance metrics of the scheduling algorithm, right, such as throughput. Okay, throughput is jobs per minute, per second, per hour. So we can actually compute this for a simple first come first serve scheduler. Okay, let's take a simple example straight from the book. We're going to have one 168-hour job followed by 168 1-hour job. Okay, so if you look at the queue, okay, so we're going to say that well in the beginning there's one job over here that needs to run for 168 hours. And then there are 168 of these guys. Each one of them will run for 1 hour. All right, so here's 168. Okay, so if we look at the throughput of the system, right, so the first guy is the 168-hour job. Okay, we don't have any choice because it was first come, first serve. We can say, oh, this is a really long job. Let's put it in the back, right? I mean, we all have the same experience at supermarkets that, this is somebody who has a, full load of grocery, right? I mean, you sit behind them, you have to wait. Okay, so in this case, right, if you draw a picture of time, okay, and over here, this is the throughput, okay, all the way until 168 seconds, you haven't finished one job yet, okay, so it's pretty much your throughput up to that point. It's almost like 0 job per second or just 0 job per hour. I mean, in a way, you are, this curve that you draw will be a slope of 1 over 168 jobs per hour. Okay, so it almost looks flat, right, because it's a, very small slope. Okay, after you get to this point, you finish one job, right, so at this point, the throughput is 1 over 168. From this point on, every hour, you get one more job finished, right, so 169, 2 divided by 169, 3 divided by 170, 4 divided by 171, etc. So at this point, you have a straight line that goes all the way up. Okay, in the end, when you finish right here, at this point, you finish 169 job divided by 336 hours. All right, so this is this point right here. It's just below 0.5. Okay, because if it's 0.5, just above 0.5, right, because it's 168 divided by 336, that's 0.5. In this case, it's a little over that. No, actually, 337, sorry. At 337, that's when this guy's finished. Okay, so performance, the overall throughput is less than, a little less than a half. Okay, so if you look at this last point, well, you can say that, well, if I have any kind of scheduling discipline, I'm going to hit this last point in the end anyways if I don't have the CPU go idle. Okay, so I can actually schedule the job any way I want. In the end, I'm going to end up with this point because in the end of 337th hour, I have to finish 169 jobs. Okay, so the question is, how do you get here? Did you get here by doing this? Did you get here from doing this? Did you get here like this? Or do you get here by doing something like that? All right, so we can sort of compute things like, throughput and waiting time. All right, so one thing that you can compute is this average waiting time. And again, this is not the same waiting time definition as a couple of slides ago. So this is the time from the time you start, your scheduling till the time the job actually finishes. Okay, so you can call this a response time. Okay, in warm-up number 2, we call the average time in the system. Okay, or the overall system time. Okay, so how do you compute this, right? For a job J, if it starts at TI, then the average waiting time is going to be TI plus capital TI is its execution time. Okay, so job J with the execution time of TI is capital TI. So then for every job, you can actually just add up, the time it starts plus the time it ends, and then you add up all that time and you divide by the total number of jobs. Okay, so that what you get is the average waiting time, and in warm-up 2, you've done this already, right? So you know how to compute this. Okay, if you compute this for our example, you will see that the average waiting time, if you add this all up, okay, it's 252 hours. Okay, well that's because the first job is a big one, right? So therefore everybody end up, so all the other job waiting for at least 168 hours. Okay, so that's why the average waiting time is really bad. Okay, you can also compute standard deviation, right? That's why we compute average, the standard deviation for the average time in the system. Okay, so you can do the same thing over here, and the standard deviation is 42.25 hours. Okay, is that high? So standard deviation, again, it shows you how widespread the distribution is, right? If the standard deviation is small, that means that everybody pretty much has the same waiting time. Okay, if it's widespread, that means that sort of the waiting time is all over the place. Okay, so if you look at these jobs, right? One job wait for 168 hours, and all the other one wait for more than 168 hours. Okay, so the waiting time tends to be spread out. Okay, so that's why you get a sort of a reasonably sized standard deviation. Okay, so this system is slow, and then it has high variation. Okay, but this is just our example. What if you're lucky? What if the 168-hour job arrive at the end? Okay, then you're actually going to do pretty well. Okay, so first come, first serve, you really don't have any control of things like this. If you make the worst case assumption, then it can be very bad. But when you're lucky, you can actually perform really well. So why do people like first come, first serve? Why do the supermarket have first come, first serve queues? Right, because it's fair. Right? If you're unlucky, you're unlucky. But at least it's fair. All right, so if you look at this waiting time equation, okay, you can rewrite it and something like that, and you try to say, well, I'm an engineer, I try to, minimize the average waiting time, over all of these kind of stuff. You can actually solve for this, and you will come up with a minimized scheduling algorithm, which says that this expression is minimized if you serve the jobs according to their execution time. Okay, if you run the smallest execution time job first, then this expression is minimized, so you have minimal average waiting time. Okay, so this scheduling discipline is called shortest job first. Okay, so shortest job first, does that make sense? Okay, if you go work for an internship or something like that, your boss give you 20 tasks to do. Which one do you work first? You look at all these jobs, you say, well, this one is short, this one is long. I'm going to work on the short one first. Why do you do that? So if your boss come by 3 days, he says, how many have you finished? You say, 5. If you finish, if you start working on the long one first, your job comes by and says, how many have you finished? You say, none. Okay, so shortest job first appears that you have good throughput. Okay, so, so on a system where large throughput, okay, is important, well, then maybe you want to run shortest job first. Okay, so if you know the execution time of every job, okay, then potentially you can, do shortest job first. Okay, if you don't know the execution time, then, then what do you do? Okay, so here's the picture of running shortest job first, right? So you would do all the short job first, right? So during the first 168 hours, your throughput is 1 job per hour, right? So it's a straight line all the way here, go to 168, okay? And then take you another 168 to do the next job, and then if you compute the average, it actually looks like a curve here, but eventually you will reach the same point where you finish, 169 job in 336. I think it's 336 and not 337. Okay, so you end up with exactly the same point. All right, so remember, first come, first serve, you get the same, you reach the same point, but using a different path. All right, so the scheduling discipline sort of actually affect, so this is the kind of throughput that you look at as you, this is kind of like a running throughput, right? If you look at this curve, any point in time you can ask, well, what is the current throughput so far? Okay, the number of jobs per second that has been completed. Okay, so so it depends on what you want. You can use a different scheduling discipline. This one, average waiting time is 86 hours, and it minimized that expression with before, so this is kind of the best you can do. Okay, so the average waiting time is 86 hours. But if you have a system that you have, jobs keep arriving, okay, and you run shortest job first, okay, what's going to happen, right? The long job never get executed. Okay, if you think about this, your run queue, right? You start with the long job first, and then a small one come here. Okay, and then as you have new jobs arrive into the system, like Walmart number 2, if you do shorter job first, they might get ahead of this job because you're doing shorter job first. Okay, so if you have a really busy system, right? Again, Walmart 2, Lambda is big. Okay, then this guy will never get to run. Okay, so if you're the owner of this job, you're going to be very, very unhappy. You say, this is really unfair, right? Operating system terminology, this is called starvation. Okay, you have a thread that doesn't get the CPU. Okay, so that thread is going to starve. Okay, so if you want to design a operating system, you want to sell it for other people, you better make sure you never have starvation. Okay, otherwise you're going to end up with very unhappy customers. All right, what if you have preemptive scheduling? Okay, so in this case, a job can be preempted, right? So therefore, what you can do is that if you look at this picture, you try to run all the way out here, okay? But, somehow you get preempted right here because either a job that's more important comes along or, you have some kind of a quota that you said that every time you run the CPU, you can only run this much, then you get kicked out of CPU. Okay, so that's like a time slice, kind of a system. Okay, then what happens at this point, you have to leave, and then since you haven't finished running on the CPU, you'll go back into the run queue, okay, and wait again. Okay, so this is the preemptive system. Okay, so we're still going to assume that we don't really, we know the execution time of the job. Okay, so in that case, we still have the same equation as before, where the shortest job first is the good scheduling policy. All right, so in that case, what would we do, right? So again, we'll do the same thing, okay, except that now we have preemption. We're going to reserve the word shortest job first for the non-preemptive scheduling discipline policy. If we allow preemption, and we always want to run the shortest job first, Well, then it becomes the shortest remaining time next, or SRTN. Okay, so again, because of that equation, this one still gives you the optimized throughput. Okay, so anytime a new job arrives, you can evaluate all the system and say, well, which job has the shortest amount of remaining time? Okay, again, you only know if you know the execution time of every job in the system. All right, so if you want to optimize throughput, then again,
The time is 21 o'clock.
The analogy of shortest job first, but now on a preemptive system. All right, fairness, as I mentioned, it's tough to describe exactly what it is. But for now, we can sort of just think about fairness at the thread level, or maybe even, I guess later on we're going to sort of generalize that to the user level. All right. In the first come first serve scheduling discipline, even though it can perform very poorly, but we know for sure that every job eventually get processed. Okay. Is there a way for a job to start in the first come first serve scheduling? Right? There's absolutely no way, right? Even if you have new arrival coming to the system, they get queued up behind other jobs. Okay, so every job gets to run. It's very fair. Shorter job first and shorter remaining time next, so even if you have preemption, okay, that will actually make the starvation problem even worse, okay, because your job will never finish, even though if your job starts to run, once you start to run, you get kicked out of CPU and then you never run again. Okay, so this is really unfair. Okay, so what is a good measure? What happened to my... Okay, anyways, there's a slide that I thought I was missing, but it's coming next. All right, so one thing that you can do is, what we know about how scheduler works, right? There's this time slicing, system that when you run on Nunkey, right, every, thread gets a time slice. It gets on the CPU. If you use up your time slice, then you get, reschedule into the run queue and run again. Okay, so this one, every job gets to run on the CPU for the amount that's equal to Q over here. And Q is known as a quantum or known as a time slice. Okay, so you have a first come, first serve queue, right? So this is FIFO. This is FIFO with what's called round robin. Okay, so when you get to the head of the queue, you get to run the CPU. Okay, if you use up your quota, you come right back here. Or you use up your quantum, you get back right here. Okay, and then this continue, going on. All right, so very simple, right? This is combining FIFO with round robin. So if you look at all the jobs over here, I'm sort of drawing the picture a little differently. Okay, so you can think about every one of these jobs. I'm going to draw it as, instead of horizontally, I'm going to draw them vertically. Okay, and then the remaining service time is drawn in this picture over here. Okay, so in that case, when I'm running a round robin scheduler, what I'm actually doing is that I'm going to serve one job at a time, right? But every time I'm going to serve Q seconds on these jobs. Okay, so if you look at this, what the CPU will do is will run this job for Q seconds, okay, and then switch to the next job and run Q seconds on this job, and then run Q seconds on this job, run Q seconds on this job, and etc. Okay, so it looks like I'm just taking a slice out of every job where the slice is Q seconds. Okay, so in a way, after one round, right, it's called round robin. After one round, I serve every job, and I run Q seconds on every job, and then, the remaining service time for every job is reduced by Q seconds for every job. All right, so if you look at this picture, which job is going to finish first? Right, I'm going to keep slicing this until I get here, then this job is going to go out first. Okay, so what does that do to the average waiting time? Well, the average waiting time is not as good as shortest job first, okay, but actually it can get really bad. Okay, because if all right, because if I have many jobs, then every job gets to wait. Right, so the first time this job goes out, how long does it take? It takes the remaining service time of this job multiplied by the number of jobs in the system. Right, it's the area of this this picture right here. All right, so that's how long it takes for the first job to go out. So all the other jobs, they will wait at least that much amount of time. Okay, so therefore the average waiting time is not that good. Okay, but then if you look at the standard deviation, the variation will tend to be a little small. Okay, because the effect of this one is basically try to even out the waiting time of all the jobs. Okay, no matter which order they come in. All right, so we're gonna sort of see numbers, pretty soon. All right, so this is, if we take this quantum, okay, and we take it to 0. All right, so basically a time slice that goes really, really fast. So we can assign, we're doing the scheduler, right? So the kernel can actually assign the timer to get interrupt every, Q, microsecond or millisecond. Okay, if we take this down to 0, then basically we're sharing the processor equally among all the jobs. Okay, and that's, there's actually a term in that, in the scheduling literature, it's called processor sharing. Okay, that's an idealized case where the Q is actually equal to 0. Okay, so you can think about, all the service time, they're like water, right? They get drained out of the system at a constant rate. Okay, this is really not realistic because, in real system, we don't want to have Q approaches 0, right? Because we have things like translation look-aside buffer. Okay, if you continue to switch from one thread to another, okay, where a thread gets to run the CPU for 0 amount of time, then basically, as soon as you run that job, you're going to get page misses. You're going to get page faults. Okay, so therefore, in this case, these jobs are not going to run very efficiently. Okay, so because of the effect of translation look-aside buffer and all kinds of caching problem, if Q is equal to 0, your system is going to perform really poorly. Okay, so therefore Q needs to be a reasonably large number. Okay, but if Q is too large, that's also not good. Okay, you're going to have some job appear to be not making any progress. Okay, so as it turns out, it's kind of tricky to sort of determine what is the optimal Q to assign to, because it really depends on what's your hit rate in the translation look-aside buffer, and also what other kind of caching are you having in that system. Okay, so some of the system will just use some sort of rule of thumb number to say that, well, I'm just going to set the quantum on at 100 microsecond or something like that. Okay, so you probably heard all kinds of numbers. Some people say, well, for the system, the quantum is 10 millisecond, 1 millisecond, or 100 microsecond. So there's really hard to figure out exactly what's the right quantum to set. All right, so if we use round robin with FIFO, after you do the analysis for our example, right, one large job followed by 160 identical job, the average waiting time, okay, so it turns out to be 169.99. Okay, so the average waiting time is not so bad. Okay, it's much worse than shorter job first, right? Shorter job first has 86 hours of average waiting time. But, it's much better than the worst case FIFO scheduling, which has 256 hours. Okay, so this one does somewhere in between. What's good thing about this round robin with FIFO is that the average deviation is 2 hours. Okay, so this is very, very small compared to things like FIFO, which is 52.25 hours for FIFO. Okay, what about for shortest job first? What is the deviation? Should it be bigger than, the FIFO or less? I mean, the shortest job first, they try to create variation, right? Because the shortest job run first, so the longest job will run, longer. So it turns out that, all the job, the variation is going to be larger. Okay, so if you want to minimize, the deviation in waiting time, you don't want to run shortest job first. Okay, but we can also just compute that, but it's missing from the textbook. All right, so those are the basic scheduling algorithm. All right, so now we're going to assume that we don't know the execution time of jobs. Okay, so for round robin, I mean, do we have to know the execution of jobs, the execution time of jobs? And we don't really have to care, right? Because we just say, well, everyone get a quanta and they finish. If they don't, they continue to go back to the run queue. Okay, so that's also sort of a good starting point for scheduling jobs, where you don't know the execution time. All right. So in this case, we're going to, say that the job will not get to run to completion. Okay, they can block for interactive jobs, right? If the user is typing on the terminal, well, then you do a read from the keyboard, and then the user don't type anything. Then you get stuck in that I/O queue for a very long time. Okay. So in that case, the system sort of divide into two kinds of jobs, right? Think about you running on NumKey. Okay, you're the one sitting on the terminal, and then other people are running simulation and stuff like that in the background. Okay, so you become an interactive user, and all the other people are batch users, or your process becomes, your login shell is an interactive, process, while the other jobs that are running the system, they are batch systems. Okay, so for your operating system implementation is concerned, who should you favor? Okay, should you favor the interactive jobs or the batch jobs? Right? I mean, you want to make the batch job has high throughput, okay, but you also want to make the interactive jobs has good response time, right? You want your system to seem responsive to the interactive user. Okay, so therefore the general thing that you will do is that you will favor the interactive, jobs. Okay, but the question is, how do you do that? Okay, do you just classify jobs? Oh, it's a login shell. It's it's an interactive job. If it's a simulation, how do you figure out it's a simulation? Etc. So we sort of gotta have a way to sort of figure out which jobs are interactive and which ones are not. Okay, so if you want to favor interactive jobs, then you can use a priority system, right? We're going to use the strict priority system. Okay, so in the sense that we're going to make our run queue into multiple queues, and this one has high priority. This one has low priority. This one has medium priority. Okay, and the scheduling algorithm says that you only run any jobs in this queue if the high priority queue is empty. Okay, and you only schedule any jobs. You only run any job in low priority if both of these queues are empty. Okay, so that's a strict priority system. Okay, so what happens is that we can actually use round robin and FIFO in every queue. If you have a job that's high priority, you run it over here, and then you do round robin with FIFO, and then you have medium and low. Okay, the problem with the system is that you have to classify jobs as high priority, medium priority, and low priority, and that's very difficult to do. Okay, if you build your operating system today, how can you tell 10 years from now, who is going to be, high priority and low priority? Okay, so a variation of this, it's a multi-level feedback queue. Okay, so you're allowed your job to change priorities. Okay, you can start the jobs over here. It's running at this priority, and somehow you say that, well, this job doesn't really deserve this priority. What you can do is that you can actually downgrade it. Right over here, you say you can downgrade it to a low priority, and then you don't like it again, you can downgrade it, etc. If a job running at a low priority says, oh, this guy needs a boost, so I can actually move him to a higher priority queue, and eventually even move to the highest level priority queue. Okay, so this is a multi-level feedback queue, and this is the kind of queuing system that Windows uses. Okay, because Windows, they would like to support both interactive user and also batch users. All right, so how do you use this? How do you decide when to bump these priority? Okay, so one of the typical use of the multi-level feedback queue is that when a thread gets created, okay, we will schedule as the highest priority, into the highest priority queue, right? So this means that in the thread control block, you will actually have a number in there to say that which queue that is supposed to use. Okay, so you started out in the high priority queue. We're going to schedule it at the highest priority to observe what it does. Okay, because we don't know if this guy is an interactive job or this guy is going to be a batch job. Okay, so how can we decide? Right, so we're going to use this very simple algorithm. Okay, so again, inside the operating system, right, we talk about LRU is the optimal the optimal thing to do for replacement policy, but it's hard to implement. So we're going to use an approximation. Okay, so over here again, we're going to sort of guess what type of job these are. Okay, so if the job use a full time slice, right, we're going to use round robin in every queue. When this job gets to run, we're going to remember whether it used up the time slice or not. Okay, if it used up the whole time slice, we're going to say, oh, you're a batch job. Okay, if you don't use up the time slice, we're going to say, oh, you are an interactive job. Right, because if you're an interactive job, you tend to block on either file I/O or terminal input and stuff like that. Yeah, so you don't usually use up your quota. Okay, so therefore we can make the decision. If you use a full time slice, then you should have lower priority because we don't then you are sort of trying to run to optimize for throughput and not optimize for response time. Okay, so in that case we would decrease your priority to move you down to the bottom. Okay, if it blocks for whatever reason, it's waiting for mutex, waiting for I/O. Then we're going to say that, hey, you are an interactive job. Okay, so in that case, we're going to increase your priority. Of course, if you're already at the highest, then you stay in the same queue. All right, is this a good way to go? Not so bad. Okay, what if, you have a busy system, okay? You're going to end up with starvation, right? So again, if you have a, operating system that jobs might get starved, then nobody's going to use your system. Okay, so we got to take care of this, the situation where, if you have a lot of jobs come and go, okay, you're going to end up with a job that's stuck at the lowest priority and never gets to execute. Okay, so what do you do, right? Over here, is that we can use a mechanism called aging. Okay, if a job is stuck at the low priority queue and never execute, so we're going to start age this particular job. When it gets to a certain age, we're actually going to promote it and then, run it at a high priority. Okay, basically we will ask this job to say, hey, prove your worthiness to the operating system by running in the highest priority queue again to see if you deserve to run at a high priority queue. So by running at a high priority queue, if it used up a full time slice, it's like, well, too bad, you're going to go back down again. Okay, but if you give out the CPU right away, well then, you deserve to run a high priority for a while. Okay, so this aging is very important so that you don't have starvation. All right, so, I guess the modern, laptop or phones or, things like that need to handle a lot of stuff going on at the same time. And you want the interactive job to run very well, right? When you press on the phone, if it takes a while to respond, you're going to go get a different phone. So usually the scheduler on these system, which both run interactive jobs and batch job, they are usually time sliced, right, running some sort of a, round robin system. They are priority based so that the interactive job gets run first. And then they tend to be, preemptive, right? If you have interactive jobs that goes into the higher priority queue, you want to kick out, other threads that are in the lower priority. Okay, so even though if you have a job at the low priority queue, right, the low priority queue only runs if the higher priority queues are completely empty. So now you have somebody running the CPU that's low priority. All of a sudden, a high priority job comes in. Well, you want to kick the guy off in the low priority queue so that you can run the higher priority jobs. Okay, if you don't do that, again, the system might not seem responsive. There are other things that you can do, right? If you really want to be a little more aggressive by making the right decision, right? So this is really coarse grain, right? Just determine whether you can bump the priority based on whether they use up, the time slice or not. Okay, you can use other information. For example, you can use something that are past history of this particular job, or for if you know the process ID, or if you know the executable path, you can actually keep track of history of the running of this particular program. Right? Then you can use that to determine how you want to schedule that that priority. Right? Because once you run this thing for a long time, you can collect statistics to say that, well, every time Microsoft Word runs, how much of the time it gives up the CPU before you use up the quota, and how much time you actually use up the quota. Okay, so now you can actually make a very sort of a long-term decision of which priority queue that it should start with, and make a better informed decision. Okay, again, you can use other information. Okay. All right, the next thing we're going to talk about is the problem with fairness. Okay, if fairness is important to you, what would you do? All right, so the interactive system, is it fair? It's not fair, right? Because it gives interactive job priorities, right? Okay, so we don't like that. If fairness is very important to you. Now, when is fairness important to you? Okay, so here's an example, right? If I have a shared server, I'm running in the cloud. My company is going to go buy a server, from some cloud vendor. Okay, so over here, this example is right. Me and my 4 friends. Okay, we buy one virtual machine. Okay, everyone contribute $1,000 towards the server. Okay, so if 5 of us, everyone contribute the same amount, I expect to get 1/5 of that, of that particular machine. Okay, I want 1/5 in every way. Okay, so the silly example, right? My friends are into threads and I'm not. So therefore, every one of them run 20 threads. So 4 of them, each one of them end up running 20 threads into the system, and I'm only running 1 thread. Okay, so I'm getting every one of them is getting 5/21 share of the processor, and I'm only getting 1/20th of the processor. Okay, so is the processor being fair? But the processor is saying that, well, I'm running 21 jobs, right? I'm not running 21 threads. I'm giving 1/21 of my power to every one of these, one of these threads. I'm being fair, right? So what are you complaining about? All you have to do is run more threads, then you can have better performance. Okay, so over here, I don't really want to worry about it, right? I mean, me as somebody who purchased, a share on this cloud server, I just want to own 1/5 of it. I don't really care how your CPU does it. In the end, I want to verify that I own, 1/5 of the CPU. Okay, so what is the scheduler supposed to do to make sure that you get 1/5? Okay. All right, so if you don't need a CPU most of the time, right, if you're running one thread, your thread is always busy, you expect to get 1/5, right? But if your thread give up the CPU because you're waiting in I/O or waiting for internet connection, well, that's too bad, okay? Then it's okay to give CPU to somebody else, okay? But if your CPU wants to run, it needs to get at least 1/5 of the CPU, right? Or everybody needs to get at least 1/5, so which means that everybody will get 1/5. All right? So what do you do, right? So there's a scheduling algorithm that's actually fair. Okay, this is called lottery scheduling, right? So the idea over here is that what I'm going to do is I'm going to issue 25 lottery tickets, okay? And I'm going to give every one of these parties 5 tickets, okay? So you get 5, right? So over here we get 5, or think about 5 virtual machines, right? Everyone gets 5, okay? And then we have CPU at the bottom. So the CPU will run a lottery. Right, over here, it has the lottery drawing. You put 25 tickets over there, and it draws a ticket out and say, well, who gets to run? Okay, so if this guy gets to run, okay, so if it pull out one of these numbers, so this guy gets to run, and then after you use up his time slice or whatever, then it pulls out another ticket to decide who gets to run. Okay, so if you pull out a ticket in a fair way, right, once you pull out, you put it back in. Okay, so overall, right, 1/5 of the time you will hit this guy, 1/5 of the time you'll hit this guy, 1/5 of the time you're going to hit every guy. Okay, is this a fair scheduling algorithm? Sure, right? Okay, right, everybody get exactly 1/5 of the share of the CPU. Okay, if you need a CPU. If you don't need a CPU, it's a different story. But if you need it, if everybody needs it, then no matter how many threads you run, you can run 100 threads over here, I don't care. You only get 5 tickets. Okay, so this is like similar to the schedule activation model that we saw before, right? We're going to say it's your business to decide which thread you run, but we're only going to give you 5 tickets, and every time we pull out one of your tickets, you get to run. All right, so in this case, we'll guarantee that everyone will get 1/5 share of the CPU if you need the CPU. Okay, all right, so how do you implement this? Right? So the problem is implementation is a little bit tricky. Doing lottery drawing to a hash table, I mean, your scheduler will have too much overhead. Okay, so we don't really want to use this algorithm to implement this. All right, so the scheduler that implements the lottery system is called stride scheduling. That's something that Linux uses. Linux uses a stride scheduler. It's in 1995, it was some operating system research group came up with a scheduling algorithm. And it added to Linux in 2007. Okay, so it took 12 years, for people to say, oh, we can use this in a real operating system. Okay, Linux actually go all the way to call it the completely fair, scheduling. Okay, because it's pretty fair. Right? All right, so this is how it works. Okay, we're going to define something. It's called stride scheduling. So we're going to define what a stride is. Okay, so the stride is, once you get to run again, how long do you wait before you run again? Okay, so that's your stride, right? So you're taking, so over here, like this is time, right? You're taking strides like this. So this is the strides that you take. All right, so for every, every job, we need to sort of figure out what is your stride length. And if you start running over here, this is going to be the next time you schedule to run. All right, so we're going to use this stride number. The stride for every thread is going to be equal to 1 divided by, it's going to be proportional to 1 divided by the number of tickets. Okay, so let's look at a simple example. We have 3 threads, A, B, C, that are running in the run queue. Okay, A gets 3 tickets, B gets 2 tickets, and C gets 1 ticket. Okay, so in that case, your stride, right, they're proportional. Then you can just do 1 divided by 3, 1 divided by 2, and 1 divided by 1. But we don't like floating point numbers. We only like integers in the operating system, right? Anybody see a floating point number in Unix? No, right? We don't like floating point numbers. Okay, floating point numbers is very confusing, and that's why in warm-up number 1 and 2, I also asked you not to use floating point numbers, okay, because that causes error and stuff like that. Okay, so we don't like floating number numbers. So what can we do to change the stride to integers? Well, we're going to multiply by the greatest common multiplier for all the denominators of all these numbers, right? So you have 1, 2, 3. The smallest multiplier is going to equal to 6. So we multiply every one of these numbers by 6. Okay, this gets 2, this gets 3, and this gets 6. Okay, so this guy is going to have a stride with the stride length of 2. This guy is going to have a stride length of 3. This guy is going to have a stride length of 6. Okay, so if you think about if we're going to schedule in cycles, this guy is going to get run every other cycles because his stride length is 2. This guy is going to run every 3 cycles. This guy is going to run every 6 cycles. Okay, does that make sense? Right, if this guy runs every 2 cycles, then it gets 50% of the CPU. Should it get 50% of the CPU? Well, yes, it's 3 out of 6 tickets, so it get 50% of the CPU. Okay, this guy run every 3 cycles, so therefore it gets 1/3 of the CPU. Well, 2 divided by 6, well, it is 1/3 of the CPU, so this makes sense. This guy run once every 6 cycles, so 1/6 is 1/6. So therefore, this stride width sort of makes sense. All right. So every one of these threads gets a stride, a stride length or width. Okay. And now we're going to use a very simple scheduling algorithm, right? Because eventually we don't want the scheduler to be too complicated, okay? Because that slows down the system. Okay. So you want a simple scheduler. All right, so what we do is that, every thread is initialized with some sort of a pass value that could be equal to the stride, okay? And then we're going to sort of schedule based on, these pass values, okay? Over here it says, well, you can actually start with any kind of stride value. In this example, I think this is the one that's used in the textbook. No, this is not the one used in the textbook. All right, anyways, we're gonna start with the stride value, but this can be any numbers. Okay, so this guy we're going to assign a stride, the pass value equal to 2. This one is going to 3. This one is equal to 6. Okay, a pass value is just a value the scheduler look at to decide who to schedule next. And the schedule is very simple. You just use the one with the smallest pass value. Okay, so you have 2, 3, and 6. It will use the smallest one, so it's going to schedule job A first. All right? Okay, so we're going to schedule the thread with the smallest pass value. So we're going to schedule this guy in the first cycle. So A gets to run in the first cycle. All right, so, and that's it. Okay, well, there's one more step. Is that once we schedule job A, we're going to increase A's pass value by its stride value. Okay, so this guy, once we schedule this guy to run, now the next time, right, so think about, the thread control block, it will update its pass value from 2 to 4. Okay? So then what we have is something like this. All right, so this guy increased from 2 to 4. Okay, and that's it. All right, so the stride scheduling is that we keep doing this over and over and over again. Okay, so what happens if we do this all over again? Okay, so next time, so in the first cycle, thread A is going to run. Okay? And then when the next time to schedule, who do you run next? Well, you run job B first, okay? And then you change this guy to 6, right? Okay, very simple. All right, and then when you're at this point, the next time you run, sorry, I guess I haven't updated this guy to 6. Okay, and then you do the same thing, right? You find the one with the smallest pass value is going to be equal to 4. You run this guy. You increase his pass value to 6. All right, and now you have a tie, right? So when you do what do you do when you have a tie? Well, you got to have some sort of a tiebreaker. Okay, we can say, well, A runs before B, runs before C, or anything like that. Okay, so you can say that, well, C hasn't run yet. Why shouldn't I run C first? Well, it turns out it doesn't really matter. Okay, all you have to have a way is a tiebreaker. Because it's a tie, you can pick any one of them. All right, so I want to sort of pick one in a certain order so that I make sure I don't have kind of a weird effect in our scheduler. Okay, so I'm going to just run A before B before C. So the next time I'm going to run A first. So A's pass value increased to 6. And now, again, I have a tie, 6 and 6. I'm going to pick B to run. Okay, and then B's pass value changed to 9. And then I'm going to get C to run this time. So C is going to get increased to 12 over here. All right, so it's a very simple scheduler. Basically, it's kind of like a priority scheduler, right? We just look at the pass value. The pass value become the priority, okay? But we only have a single queue to run this thing, okay? All right, so if you look at this cycle, right, once I get here, 8, 9, and 12, I'm going to repeat all over again, starting from this guy, et cetera, right? So this is one cycle, okay? In this cycle, how many times does A run? 3. How many times does B run? 2. How many times does C run? 1. Exactly the same as the number of tickets that it has. All right, so the strike scheduling, basically it implements the lottery scheduling in a very, simple and straightforward approach. Okay. All right. What about if you have a new thread that comes in? Okay. The new thread will take the global pass value, whatever the current smallest value is. You give that to the new thread. Okay. You're probably going to run it first. Okay. I mean, again, you've got to break ties. If there's a tie with it, you're going to see which one has which one wins. But the idea here is that the new thread gets to run fairly quickly. Okay. What about the case where, you have a thread that's nice to the CPU by not using its quota, okay, not using its quantum? What do you do? Okay, so over here, what you can do is that, we're going to assign how much of the quota that they actually use. Okay, it's going to be between the numbers 0 and 1. Instead of increase by its pass value, if you use less than the entire quota, you're going to increase your pass value to be F times the strike width. Okay, so it's as if that you are, you're receiving a higher priority because you're being nice to the whole system by not using the quota. Okay, so again, well, you're going to end up with a floating point number, right? Floating point number is bad, right? So again, we're going to round it to some kind of an integer number. Okay, so it's not going to be exactly, fair, but then we want to be nice, to jobs that are nice to the system. Okay, so in this case, we end up favoring interactive threads. Okay, because the interactive threads, if they don't use up its quota all the time, then they're going to keep running over and over and over again. Right? And hopefully every time it runs, it gives up the CPU right away. So it's all good. Okay? All right. We're going pretty fast. So the next thing we're going to talk about are real-time jobs. Okay? So I'm going to talk about slightly different things in the textbook. The textbook have the section on the scheduling of real-time job. They use something called a meter processor, and I think it's a little confusing, so I'm going to use sort of a straightforward way of talking about how to schedule this. Oh, wait. Now, I can't remember whether the meter processes, is that their explanation for strike scheduling, or their explanation for for the real-time scheduling. I think that's their explanation of strike scheduling. Okay, so anyway, so we use a sort of slightly different way to describe that. All right, and then now we come to for the sake of exams, okay, please skip the section of meter processors in the textbook. Okay, if I ask any questions on strike scheduling, you need to be able to do the algorithm that I just mentioned. Okay, somebody asked a question about what's on the final exam. I said, well, there might be things you have to calculate. Well, I mean, calculating a schedule is kind of like calculation, right? So you should expect, some of the problem might be related to, calculating, schedules that are related to this lecture. All right. So the last part is, for the scheduling algorithm is talking about scheduling these real-time systems. And we're going to talk about hard real-time system, right? Because the soft real-time system, we can use the previous way to do these things. And if it missed the deadline, it's really not that big of a deal. So in this case, the hard real-time system, right? I mean, these are nuclear reactors, okay, that we're trying to schedule, or some kind of a device controller. And then, your set-top box, somebody might have some fancy set-top boxes. I heard that. I don't own one. I heard people who are really into horse racing, they will buy a special box. They can plug into the, into their internet. They can actually watch, what's going on, at the track, and be able to purchase, to put bets, instantaneously. Okay. So for those people, if the system is not real time, it has a hiccup, and then when they try to make a purchase, they miss the deadline. They're going to be very upset. Okay. So those not as hard real time as nuclear reactors, but some people will consider those kind of stuff, hard real time system. All right, so in this case, you want a specialized processor and you want a specialized operating system with a specialized scheduler, okay? Because you want to make sure, because not missing deadline is the most important thing, okay? So you need to know everything about your machine. You need to know the running time of your every job, and you need to know the characteristic of every job, okay? So assuming you all know all that, what kind of a scheduling algorithm you will use, all right? So these jobs have known chores and duration, okay? So this system, if they only run 5 kinds of jobs, that's all it runs. It doesn't run anything else, okay? And every job, how does it behave, it knows exactly, okay? We need to come up with a schedule that satisfies all the constraints because every job has a deadline, okay? We're going to look at the case for a uniprocessor, okay? Because the multiprocessor is a little complicated. Some of them are, there's really no efficient algorithm that can figure out what is the schedule that can satisfy all the constraints. Okay, we're going to focus on the uniprocessor. We're going to look at 2 algorithms. One is called earliest deadline first, EDF. So every job has a deadline. Okay, if you had taken CS570, you've probably seen a proof that under certain condition, earliest deadline first will give you the optimal solution. Okay. But again, we're not going to sort of focus on that. Just to talk about, if you look at all the jobs, every job has a deadline. You sort them in a queue, and you just start running these jobs based on the deadline. Okay, as it turns out, that's a very good scheduling algorithm. Okay, does it guarantee to meet all the deadlines? Well, so basically, you have to run your scheduling algorithm, right? Because you know every job that are in your system, right? So you can run the scheduling algorithm before even you build the machine, okay, and try to make sure that you can actually satisfy all the deadlines. Okay, if you want to add a job to this machine, right, you said, well, now it's doing 5 things. I want 6 things in this box because I have extra capacities. Okay, so again, you run your earliest deadline first algorithm, make sure every job meets the deadline, and then you can go ahead and build it. All right. The second one is it's called rate monotonic scheduling, okay, and these are for cyclic chores, okay, so these are for periodic tasks, okay, so most of these monitoring system, control nuclear reactor and stuff like that, all they run on these systems are cyclic jobs, okay, so they basically every job runs in cycles, okay. So what does that mean, run in cycle, right? So for example, every job has 2 parameters. One is TI, one is PI. Where TI is the execution time of job I, and then PI is the period of that particular job. Okay? So for example, a job is required to execute for 2 seconds, that's the execution time. Every 6 seconds, that's its period. Okay, so this one says, right, this one is going to use up the CPU, right? If it doesn't miss a deadline, this guy's going to use up 1/3 of the CPU, right? Because every 6 seconds, it's going to use up 2 seconds. Okay, so this guy has a duty cycle, right? Duty cycle of 33%, right? 33.3%. All right, so if you add up all your jobs and add up all their duty cycles, and if it's bigger than 1, then you know that you cannot run on the CPU. Okay, so there's some simple way just to verify that there's no way to schedule all these jobs inside a machine, because if you add all their, all the TI divided by PI, if you sum them all up, if this is greater than 1, then forget it. Okay, if it's less than 1, maybe it's hopeful. All right, so we're going to see some of these things. The assumption, right, is that we know everything about our system. Over here, right, the scheduler, right, over here says, well, interrupt doesn't interfere too much with scheduling, and if it does, you can subtract that ahead of time, saying that I'm going to do a worst case assumption. All the interrupt is going to take this much capacity out of my CPU. Okay, so therefore, they're the highest priority tasks. They take everything away. So you can do that. And also, we're going to sort of assume that the execution time is entirely, predictable. Okay? In reality, that's going to be very difficult to predict, right? Because you have all the other things, right? Like, caching, paging, translation, look-aside buffer, all these kind of stuff is going to make it difficult to predict. Okay? But if you're going to build a little controller, are you going to use, paging? Are you going to use virtual memory? Maybe not. Okay, if you really want to make sure, because meeting the deadline is the most important thing, then you try to minimize these kind of effects as much as possible. Okay, or you can also make sure that you always do the worst case analysis. Start with a flushed, translation look-aside buffer, or try to flush it every time. Okay, so you can have a more predictable performance in every task. All right, so let's look at the rate monotonic scheduling first, right? So these are the ones that schedule periodic chores, okay? Every job I has a period PI, okay? And then has a processing time of TI, right? So if you do this, if you add up TI over PI, right, that's a duty cycle. If you add them all up for all the jobs, and there are N jobs inside your system, right, N jobs. Okay, if it's less than 1, then over here it says feasible. Okay, so feasible means that there might be a way that you can schedule this, but you might not be able to find a schedule that will fit all these jobs. Okay, you just know that it's kind of feasible. All right, so rate monotonic scheduling is a simplified algorithm. Okay, to try to say that, well, we don't really do earliest deadline first. It requires sorting and stuff like that. That might be a little too complicated. So we want something simpler. Okay, but when you have simpler, you're going to sacrifice something. Okay, so what you sacrifice is that when you add this all up, if it's close to 1, then chances are you cannot schedule all these jobs. Okay, but the advantage is that, you will be able to run a very simple algorithm. Okay, and the way that you schedule this is basically use priority scheduling. Okay, every task I or every job I is handled by a thread with priority 1 over PI. Okay, so the longer the period, if the period is really large, then 1 over P is going to be really small, then that job has very low priority. Okay, if the period is very, very small, okay, then so if the period, if the cycle time is going to be small, right, this guy, let's say that when it runs, we have 6 seconds, right, it needs to run for 2 seconds, 2 seconds, and this guy runs 2 seconds, okay? The smaller the duty cycle is, it doesn't really care about the execution time. Okay, then there seems to be more urgency to schedule this job. Okay, so this scheduling policy basically just look at the priority and ignore the execution time. All right, and it's preemptive. Okay, if you have a job at higher priority that needs to run, it will preempt whatever that's running in the processor. Okay, preemptive and strict priority queuing. I guess there's some theory that go behind this to say that if you add up all the duty cycles, if it's less than this equation, where n is the number of jobs, okay, then you guarantee that you can schedule all the jobs with rate monotonic scheduling. All right, so this one is very, it's really useful because what happens is that all these numbers, you plug them all in, you add them all up, and then you know how many jobs you are. You can compute this number. If this number is less than that number, this number is going to be less than 1. Okay, when n goes to infinity, this will be equal to 1. But when n is, less than infinity, this will be less than 1. Okay, so if you know that this equation fits, then rate monotonic scheduling will schedule all your jobs. Okay, so it's an easy way to go, right? This can never be equal to 1. In the limit as n goes to infinity, this is equals to, this expression equal to natural log of 2, and natural log has the base of 2.8 something, right? So this is, less than 1. All right? So if you add up all this, if it's less than natural log of 2, there's a good chance that you can say, I guess over here you can actually guarantee that the rate monotonic scheduling is going to work. All right, so we're going to look at an example to see how this is done. Okay? We have 3 jobs, right? Job number 1, okay, so job number 1, the TI, so T1, right? T1 is equal to 1.5. Sorry. T1 is equal to 0.5. T1 is the execution time, right? Okay? And P1 is equal to 1.5, right? Every 1.5 seconds, it runs again. Every 1.5 seconds, etc. Okay? I should write it down here. T1 is equal to 0.5. P1 is equal to 1.5. Okay? So P1 over T1, this is equal to 1/3, right? Okay, this is a 33% duty cycle. T2 is going to be equal to also 0.5, and P2 is equal to, it runs every 4 seconds, right? This is equal to 4. So this is going to be equal to, duty cycle is going to be equal to 1/8. T3 is going to be equals to 1. P3 is equal to 2.5 seconds. Okay, so this is equal to 2/5. All right, if you add them all up, it's going to be less than that equation. So this one says, you know, rate monotonic scheduling is going to work. Okay, guaranteed to work. Okay. All right, so how do we schedule them? Okay, so the rate monotonic scheduling says we just schedule this job the way they are, okay, in this particular picture. Okay, so also, by the way, so let's just add them, right? If you add them, what do you get? Right, 1/3 plus 1/8 plus 2/5, right? That's equal to, the smallest common multiplier is going to be equal to 120, right? So 120, right? So it's 40 plus 15 plus it's 48. Okay, so this is going to be 103 over 120. All right, so this one clearly is less than 1, right? So there, you know, there's hope. All right, so we're gonna just schedule them, you know, as is. So, you know, the way we're gonna look at it is, right, if you are the highest priority, okay, I guess we should go to the previous slide. Okay, which one has the highest priority? Right, the one with the highest priority is the one with the largest fraction, right? So this is 0.3, this is this 1 over, sorry, oh, okay. So, yeah, the priority of the first one is 1/3. The priority of the second one is 1/4, right? Because I can only look at the P, right? So this one is actually equal to 2/3 for the priority, right? It's 1 over P1 is equal to 2/3. 1 over P2 is equal to 1/4, and 1 over T3 is going to be equals to 2/5. All right, so I was looking at the duty cycle. That's the wrong thing to look at. So therefore, this guy is the highest priority, okay, and then followed by this guy, followed by number 3, and then followed by number 2. Okay, so since you're running strict priority, that means that if you're running job 1, then you never see any of the other jobs. Right? Because that's what the highest priority means, and that's what preemption means. Whenever you want to run job 1, it gets to run. Okay? So we might as well just lay down all the job 1 right now, okay? Because that whenever they want to run, they get to run. Okay? And then we're going to lay down the second priority jobs, right? Because when the second priority job, the only thing that it sees is the higher priority job, and it's not going to see any of the lower priority job. Okay? So now when we try to schedule job number 3, at this time, what happens? Okay? What will happen is that if you try to run job number 3 right here, well, it's going to get preempted by job number 1. Right? So therefore, 3 gets to run right here. Okay? This job, if you schedule it, right, it's going to run from here, and it's going to get bumped off by job number 1, and then it's going to continue to execute right here, so it looks like that. The next job is going to run right here. This guy is going to run right here, and etc. Okay, so you can actually figure out, right, because we have strict priority, we know exactly when job 3 is going to run. Okay, very simple, right? And then finally, job 2, if we schedule this job right here, when does it get to run? Right, it doesn't get to run until right here. It's a good thing we have a hole right there. Okay, did it finish before its deadline? Well, this guy's deadline is right here, right? So that actually works. Okay, this guy will get to run right here. This guy will get to run, you know, whenever it gets to run. All right, so we can actually figure out the schedule, you know, fairly, you know, easily. All right, so, you know, very simple, right? Now if we add another job, okay, job number 4, the duty cycle is going to be 0.5 over 4.5. It's going to be equal to 1 over 9. What we had before is 1 over 3 over 120. If we add 1/9 to it, turns out it's still less than 1. Okay, but in this example, if you try to schedule it, right, it has the smallest priority, right, because it's 1 over 4.5. That's the smallest number. Okay, so it's going to see job number 1, 2, and 3. So in this case, if you schedule this job right here, okay, it's only going to get to run right here. Did it miss the deadline? Well, it's a periodic task. It has to finish right before the next time it has to run again. So therefore, it violated the deadline. Okay, so even though it's less than, you know, if you sum up all the sort of the duty cycle or the utilization of CPU, it's going to be less than 1. But in this case, rate monotonic scheduling failed. So therefore, what we're going to try is the earliest deadline first. Okay, as it turns out that this one, earliest deadline actually works. Okay, so let's try the earliest deadline first, right? So very simple. So over here, this is rate monotonic scheduling. Okay, so we're going to look at jobs as they come in, okay, and try to figure out who to schedule first. Okay, so in the beginning, when at time 0, job 1, 2, 3, 4 all has arrived. Okay, you look at the deadline, right? Job 1's deadline, well, job 1 has to run right before this time, because this is the next time job 1 gets to run again, right? So therefore, that's the deadline. Job 2's deadline here, job 3's deadline here, job 4's deadline here. Earliest deadline first says schedule job 1 right here. Okay, then this guy's gone, right? And then you know that the next job 1 is going to arrive right here with the deadline that's right here. Okay, so we're going to schedule this job. Okay, this job is the one that's red, right? We schedule it. Okay, so now at this time we have these 3 jobs right there. At this time, we shouldn't really look at this one because this job hasn't arrived yet. All right, so if we are sort of scheduled on the fly, we only deal with what we have right now. Okay, so at this time, we have schedule all the way up here. Okay, we're going to look at all the jobs in the system. All we see are 2, 3, and 4. The earliest deadline is number 3, so we're going to schedule job number 3 over here. All right, so now we have this picture. We schedule number 3, and then we are right here. Okay, so at this time, what do we have? Job number 1 comes into the picture, right? So we have to take job number 1 into consideration. Okay, now we have 3 deadlines right here. Okay, the earliest deadline is actually number 1. Okay, so over here, we're going to run job number 1 right here. Okay, because that's the earliest deadline. Okay, we pick this one, we schedule it right there. Okay, and now we are at this time. Okay, so the only job that we see right now are still job number 4 and 2. Okay, so we're going to schedule the earliest deadline, which is job number 2 right here. Job number 2 go into the CPU scheduler. Okay, and now at this point, job number 3 is starting to appear, right? We're right here. Job 3 has arrived at that point, so we have to add to that. And now we're looking at 2 deadlines, right? 3 and 4. Number 4 wins, so we're going to schedule job number 4 over here. All right, so as we schedule, we see whether every job makes the deadline or not, right? Okay, so job number 4 is scheduled right here. Okay, and now we are right at this time point. Job number 1 comes into the picture. Okay, we have 2 deadlines. Earlier deadline first, we're going to schedule job number 1. Okay, and then we are right here. Okay, at this time, the only jobs in the run queue is going to be job number 3, right? So that's the one we're going to run. Okay, so now we're right here, right? At this point, okay, job number 2 comes in. Okay, so early deadline for there's no more priority, right? This guy, job number 2, number 3 is running over here. Okay, number 2, even though it comes in, it doesn't preempt anybody. We don't have to look at its priority. Okay, because the priority becomes the deadline. Right, so the deadline is the priority. All right, so we're at this point, again, 1, 2, 4 become visible. Look at these 3 deadlines. Job number 1 is going to go into the CPU first. Okay, and then we are at this point, we have 2 and 4. Okay, and also number 3 comes into the picture at this time. We have 3 deadlines to look at. The earliest deadline said we're going to schedule job number 3. Okay, it goes into the CPU, and now we're right here. Number 1 also become visible. Okay, we're going to schedule these 3 jobs. Number 1 wins, goes into the CPU. Okay, so at this time, we still have 2 and 4 we haven't scheduled. Number 2 wins, goes into the CPU, and then at this point, the only thing we have is number 4. So number 4 gets scheduled right here before its deadline. All right, so you can see that this scheduling algorithm is a little messy, right? But you can do this on the fly as job comes in. Okay, but of course, it's very dangerous to do this on the fly for a nuclear reactor. So you should do this offline, but you can do the analysis as job, So this can all be done inside a simulator. Okay, if you know the execution time of every job, you can simulate this and make sure every job won't miss their deadline, right? All right, so I'm going to continue to go, blah, blah, blah. Right? You get the idea. Okay, so in the end, every job nobody missed their deadlines. Okay, so and the reason in this case is that because if you sum up all the utilizations, it's less than 1. So therefore, there is a chance that the earliest deadline first might work. Okay. Okay, but again, there's no guarantee that earliest deadline will work. That's why you have to run through the simulation. That picture, all the jobs that started at they all synchronize when it starts, but they don't really have to. But as it turns out that so this is called a phase problem. You can actually start at a different time. But as it turns out that there are ways to get around it, but we're not going to get into it. All right, we are getting towards the end. We're going to look at a couple of more. So now we're done with all the schedulers that the textbook cover. Then we're going to look at a couple of implementation issues with scheduling, and of course you're going to see things like priority inversion and those kind of stuff again, right? Because those things keep popping up. All right, we're going to look at this example. We have high priorities thread. Okay, so there's high, medium, and low, right? Thread A over here, thread C over here, thread B over here. Okay. A is blocked on the mutex, number 1, and number 1 is held by thread number C. Okay, so A is waiting for C. Okay, what is C waiting for? Well, C is waiting for the CPU. Okay, C is ready to run. Okay, but unfortunately, B is also in the run queue. Okay, thread C cannot run because the medium priority thread B is running. This guy is running in, all right, so if you look at the run queue, right, run queue over here, we have both, B and C. Okay, but I guess, the run queue actually are priority, right? You have B over here, you have C over here. A is not in the run queue, A is somewhere else waiting. Okay, so if you're the scheduler, what do? Right? You schedule to run B. Okay, A is very upset, right? Because A say, hey, I am very important. I have priority, number 1. Okay, so A is going to claim that the scheduler violate the agreement because this is a priority inversion. Okay, even though the scheduler says, well, you're blocked by thread C, that's your problem, right? It's not my problem. So by the way, how can this happen? I mean, clearly, if you have a multi-level, feedback queue, a job can move up and down and stuff like that. So you're going to end up with, one thread, waiting for a low priority queue, for a thread that's in the low priority queue. Okay, so even though you're the programmer, when you program these two threads, they have different priorities, or they sort of have the same priority, but once they get into the scheduler is going to deal with them the way the scheduler wants to deal with them. Okay, so at some point, sort of what the user want to control. So like what I said before, right? When you have P threads, you want to set up priority. When you get scheduled inside the CPU, inside the kernel might not be able to honor, exactly your scheduling priority, because once you're done in the kernel says, what user thread priority? I don't know about user thread priority. I'm the kernel. I worry about kernel thread priority. All right, so over here you're going to end up with, so this is kind of an example of you can actually claim that this is a priority inversion problem, okay? Because thread A, if you're running thread C, well, the thread A is pretty happy, right? Because thread A is waiting for thread C. So if you run thread C, thread A says, well, I'm supposed to wait for thread C because it's holding a mutex that I need. So I want thread C to finish as soon as possible. Okay, so thread A is very happy to wait for thread C, but thread A is not happy to wait for thread B. Okay, so how do you solve the problem? Right, you solve the problem like in human society, right? This is big boss, right? It's waiting for, some low-life, employee to, finish something. So the big boss says, well, here's my, car keys, show this to people that says that, you have priority. Okay, so the idea over here is that you basically want to promote this guy to run at the priority of thread A. Okay, so that solves the problem, right? So certainly in this example, so this is called priority inheritance. Okay, if you wait for a low priority job, then whoever you're waiting for get a bump in their priority. Okay, so this way thread C will actually get to run first before thread B. Okay, so can thread B complain and say, hey, thread C doesn't have the right priority? They say, well, but thread A lands its priority to thread C, so thread C gets to run at the high priority. Okay, so in this case, you solve this particular priority inversion problem. Right? So as it turns out that when you do something like this, you're going to be careful because, you do something like this to handle a particular situation. Okay? But as it turns out, things can get a little more complicated when there are more threads getting involved and where the priority schemes get a little more complicated. Okay, so anyways, the priority inheritance, I guess I sort of mentioned before that operating system research, even today, they're dealing with priority inversion problem. Okay, so clearly, these problems are not solved by this very simple approach. Okay, once you plug this hole, another problem will pop up with a different kinds of priority inversion. Okay, so this is just like doing deadlock and stuff like that. If you have a procedure to avoid this, that's great. Otherwise, if you have a sort of a simple-minded approach, you're going to end up with problems somewhere else. All right, so the textbook talk about some other problem can happen. You have
The time is
cascading
22
inheritance,
o'clock.
and we're not really going to get into that. Okay, so the simple approach doesn't really solve the entire problem. Okay, priority inversion can be complicated. Another point about I guess we mostly focus on uniprocessor. What about multiprocessors? Okay, can we dedicate a processor to important threads? Okay, I don't know if you heard about it. The 128 core processor is coming. Okay, you're gonna have one of these guys have 128 cores on them, right? In a few years. Then every important job could get their own processor, right? Okay, so you have multiple processors. Some of these stuff becomes sort of easier to deal with. Okay, but today we only have 4 processors. You have a lot of important jobs, and you sort of have to worry about how do you really assign this important job to multiple processors. Okay, interrupt handling, they're all very important. Okay, maybe you want to dedicate one processor just to handle interrupts. Okay, maybe that's a good way to go. Okay, Windows, do something called the processor infinity mask. Okay, to try to improve the scheduling on the multiprocessor system. Solaris has something different. We're going to sort of briefly look at this a little bit to see what cache affinity mean. Okay, if you have multiple processor, right? One thing that you will think about is that you have a single run queue, right? You have the option to have multiple run queues or single run queue. I guess when we talk about chapter 5, we said, well, maybe you can use multiple run queue and run every idle thread in every queue. But why would you want to do that, right? Because processor gets idle. Okay, so running an idle thread is really not that great because that means that you have a CPU that went idle. Okay, if you have other CPU that are busy and one CPU that's idle, well, maybe you should move that job from the other thread, the other processor, or the other queue into this processor. Okay, so therefore the solution is to do something like this, to have a single queue with multiple multiple CPUs. All right, so this seems to be, and if you want to optimize CPU utilization, this is what you would do. All right, so what does this picture look like? It looks like the bank, right? When you have the bank, you have one bank line, a bunch of tellers that are working over there. Why do they do that? Okay, because it optimized, teller utilization. People study queuing system, analyze these kind of choices to death, and this is the way that you optimize utilization on all the CPUs. Okay. But of course, the problem is, we have caching. All right. So if you have a thread, this thread you try to schedule, okay, this CPU becomes, available. You schedule this thread onto the CPU. Okay. After it runs in that CPU for a while, okay, it likes to run in that CPU, right? Because there might be some on-chip cache that has some of the data that belong to this particular thread. Okay, if you schedule this onto another, onto another CPU, well, then this guy will have to go through some of the faults. Right? So again, it's not just the translation look-aside buffer, but with all the other, caching that you can have inside the CPU. So if you run it on a different processor, then you have to bring in those data, and that can take much longer compared to if you schedule this, this thread right into the original CPU that you assigned to it last time. Okay, so therefore, what you want is you want the the CPU you want the thread to remember which CPU that they run on, so that next time they can run on the same CPU. All right, so in that case, in the thread control block, you will add some kind of a flag there to remember which processor they run on. Okay, so this is called cache affinity. All right, so this way you can maximize the utilization of all the CPUs. Okay. So one way is to do something like that, okay, is that for every thread you remember where they are, but then, the picture doesn't really look like this anymore, right? if you have the head of this thread over here that wants to run on the CPU, but the CPU is busy, okay, another guy over here, become free, what do you do? Okay, so you can take the next guy out of this queue, but pretty much you are basically implementing this, this particular scheme. Okay, so if you really want the thread to remember which processor that need to run on, well, one way is to build a separate queue so that every time your thread is ready to run, you look at the thread control block, you say which CPU do you want, and then you schedule that thread into that particular queue. All right, so to solve the cache affinity problem, you will use this particular approach. But again, the problem with this particular approach is that you end up with one CPU getting idle because this queue will be completely empty, and while all the other queues are completely full. Okay? To solve that particular problem, if you implement cache infinity, one thing that you have to do is that once in a while, okay, so the solution to this problem is that once in a while, you may have to perform load balancing, so the CPU, so the operating system has to intervene and move some of these threads onto another queue, so do some load balancing so that all the queue have about the same number of jobs. All right? Okay, so anyway, so that's sort of one, so these are the two extremes, right? One is only one queue, and the other one is using one queue per CPU. Okay, so what about something in between? So as it turns out that Solaris actually does something in between. Okay, they have pool of processors. They call this the processor sets. So you group the processors together, and then you use one queue per processor's set. Okay, so that the thread can remember which processor set to go to, and this way you have a tendency to do less load balancing. Okay, load balancing is a little bit tricky. You have to do, how do you interrupt the entire, system? You have multiple CPU running. You basically have to stop all of them. Well, how do you stop all of them? Right? We remember the TLB shoot down algorithm, right? So that's one way to sort of stop all the processors. Okay, and only when it's safe, and only at that time you can sort of move all the jobs around. You don't want to move the jobs around when something is running inside one CPU. All right. So anyway, so this is Solaris' approach to this problem. Okay. Finally, sort of briefly want to mention what system you popular system use, and I sort of already mentioned some of these things. In Linux scheduling, these days, a lot of systems, they're compliant to the POSIX system, the POSIX specification. The POSIX, P threads, the POSIX thread, right? They specify how the user's thread is supposed to behave, one of the APIs that you have to satisfy. So if you want your system to be POSIX compliant, why do you want your system to be POSIX compliant? Okay, well, if your system is POSIX compliant, then application running in your system, if they want to run on a different system, all they have to do is to recompile, and they can run on a different POSIX compliant system. Okay, so maybe the other one has completely different implementation. On your system, you're implementing threads in the kernel, and the other one implements threads in the user space or something like that. But if they're all POSIX compliant, then all you have to do is to do recompile, and it will run on a different system. All right, and the POSIX actually require scheduling in the operating system to have 3 different queues. They didn't really say that exactly what scheduling discipline you have to do, but they do require that you have at least 3 scheduling priorities. One is the highest priority, and this one is for real-time jobs. And this, in this case, job running in this queue, they have infinite quantum. Okay, so basically, jobs running these things is as if you're doing non-preemptive scheduling, right? So this is the first come, first served queue. Once you start running on the CPU, nobody can preempt you. Okay, so this is the higher priority job. So it's real time. You can even use it, I think, for interrupt handlers, something that's higher than the priority. Then they have the second one, which is running, sort of soft real-time jobs. This one is called, I guess they call it the round-robin scheduler. These are real-time. It has priority over, the third class. So over here, they have quantum that can be adjusted. Okay, and then everybody else runs in the last queue, and this is the normal scheduler. And as I mentioned before, Linux uses Stripe scheduler, and this is where they use Stripe scheduling. Okay, I guess the textbook actually talks about a little bit about the history of the third type of the lower class scheduler. They have some old scheduler. They have some kind of called the order 1 scheduler. So again, order 1, you say, well, order 1, isn't that really, really fast? Okay, so order 1 meaning that it's independent of number of jobs in the system, but you still might have a big constant that you're multiplying by. Okay, so even though it's order 1, doesn't mean that it's sort of the best scheduler. And later on, they use, I guess in 2007, they decided to use strike scheduling, and they called this the completely fair scheduler. All right, and in Windows, okay, Windows want to handle all kinds of jobs, right? They want to make their operating system as general as possible. And they want to handle real-time threads. They want to handle multiple processors and stuff like that. And Windows end up using a multi-level feedback scheme. Okay, they have 32 priority level, right? And I guess we saw before that the interrupt. These are basically the interrupt priority level. Okay, but, all the top ones that are all interrupts, and the real jobs are actually running at the bottom. Okay, they designate the top 32 for real-time jobs. Okay, and inside over here, I guess every job can take one of these 5 priorities. So there are 5 queues over here, and again the job move up and down according to whether they use up a time slice or not. Okay. Down here, these jobs again they are depends on what kind of interrupt they are that categorize which one they belong to. Okay, and again within every one they use multi-level feedback queue. Okay, so Windows really they believe in multi-level feedback queue and they use this all over the place. All right, so I guess I'm done with scheduling, and I guess this is all I want to talk about as far as coverage is concerned. I'm going to briefly mention that, in the lecture slides, I have this thing, shared library. I said we'll go over this 7th after chapter 7. I guess we don't have enough time to cover that. We need at least, 45 minutes to cover that, so we don't have that time. So the final exam is not going to cover, shared libraries. So basically, we're going to cover, everything from chapter 1 through 7 minus everything that's covered in the midterm, and also add, kernel 2 and 3 into it. Okay, I have posted the coverage yesterday, except I made a, wait, hold on. Let me refresh this page. I have to refresh this page, right? Okay, so over here, right, the coverage is chapter 4, except the first part on a, I think it's called a simple system, right? That one is skipped. Otherwise, it covers the rest of chapter 5 all the way through 7. All right, and again, click on these links to see, what kind of questions are being asked. And the final exam is next Monday, and it will be in the same room as the midterm exam room. The same kind of policy, closed book, closed notes, et cetera, and we'll be assigned seats. And make sure you bring your ID. And again, if everybody shows up, probably not gonna, check the ID. All right. Okay, so I guess that's it for the semester. I'll see you guys on Monday. I'll still hold office hour today, and then I guess next week there will be no more office hour. So if you have any questions, feel free to send me email. Anything about the kernel, send me email, post to the class Google group. All right, see you guys on Monday.
That concludes this lecture of CS 402 with Professor Cheng. It's Wednesday, July 30th, 2014, and from your studio operator Rex, have a wonderful week. Happy Hump Day.